we introduced some gauge bosons, A mu A and B mu. We then also introduced a Higgs field, which obtained a vacuum expectation value that broke both of those symmetries. We solved for the mass eigenstates, and those turned out to be a massless photon, a set of two electrically charged heavy bosons called W, and an electrically charged neutral boson called Z. We then derived the effective Lagrangian for weak interactions that would come when you integrate out W and Z. And more or less by construction, because these are vector spin-1 particles, that effective interaction was of the current-current form. That is J plus mu, J minus mu, plus J3 squared, with a coefficient G squared over 2mW squared. And we made use of the fact that the model has a relation between the W mass and the Z mass to get the coefficient 1 here. And then we also got a slight modification of this form where a parameter SW squared appeared here and the electromagnetic current inside the square. And this, you remember from last Friday's lecture, is the form of the weak interactions which is tested at low energy. This part giving rise to beta decay, muon decay, all those well-studied things. Also, as we saw, and as you guys are studying in the problem set, deep and elastic neutrino scattering, charged current neutrino scattering. And this term gave rise to neutral current neutrino scattering. And I showed you at the end of Friday's lecture that with that you can determine this parameter SW squared, and it turns out to have a value about 0.23. So now let me just do a little cleanup here to get some formulae that will be useful to us in this lecture. When we wrote the phenomenological weak interaction theory, what we had here is 4GF over the square root of 2, where G is the Fermi constant. We also got the formula that E is equal to G prime over G squared plus G prime squared. So if you square this expression, it turns out to be the following. Alpha is equal to G squared over 4 pi divided by the sine of the weak mixing angle. That's also G prime squared over 4 pi times the divided by the cosine of the weak mixing angle. I think in this lecture, I'm going to use a lot the terminology alpha W is equal to G squared over 4 pi. So this basically measures the strength of the weak interactions, the intrinsic strength. What's in here is something that's proportional to 2 powers of G and the mass of the W. The weak interactions are weak because the W is heavy. But the intrinsic dimensionless strength is given by this parameter. Now this, as you see from this equation, is equal to alpha divided by the sine squared of theta W, or SW squared. And now it's interesting to evaluate this. Let's put in here the right number. And for this, I'm going to put in 0.23. What is the right number to put in for alpha, by the way? Sorry? No. We discussed this already. We're talking about a mass scale now of 100 GeV. So, yeah, the right number is 129. And now if you take this ratio, you get a number here which is something like 1 over 30. So it's still a very weak coupling. Certainly a factor of 3 weaker than the alphas that we've been talking about in QCD. It's not a minuscule coupling, but it's weak enough that perturbation theory is going to be a very good approximation. Okay, now, if I set these two guys equal to each other, I get another interesting formula. G Fermi over the square root of 2 is equal to G squared over 8mw squared. And actually, I can solve that for mw, and I'll get the following formula. mw is equal to, let's turn this into E squared, 4 pi alpha divided by 4 root 2 G Fermi times SW squared. So the Fermi constant, remember, is something like 10 to the minus 5 in GeV units. It's in the denominator, so we're going to get 10 to the 5. There's this alpha here, but SW, so something like 10 to the 4 when we're done. When we take the square root, we're going to get about 100 GeV. And so the answer in detail is 80 GeV. And you folks remember that mz is mw over the cosine of the weak mixing angle. So that's going to give something like 90 GeV. So this is already a pretty interesting story. From low-energy weak interactions, we can measure, and the idea of the unification of weak and electromagnetic interactions, that's what this formula represents, we can actually predict the mass scale at which we should find the W and Z particles. And then it's an interesting question to, well, go there and see if they actually are there. And so this is something that was done for the first time with antiproton collisions. The UA1 and UA2 experiments at CERN were done with a facility where antiprotons were made from colliding protons with the target. Those antiprotons were cooled, a real technical feat perfected by a fellow named Simon Vandermeer, who won the Nobel Prize for that achievement. So you get these antiprotons which come out over all of phase space. You collect enough of them that you can put them in an accelerator, and then you run them around the accelerator, and then you have literally a Maxwell's demon operating on them. So every time it comes around, you measure the phase space distribution, and then you perturb with microwaves the energy of the particles in such a way that the phase space distribution is contracted. And of course, it's causal, because the antiprotons are going around a ring like that. You measure them here, and you deal with them here, and they take longer to get around. So it's actually feasible, although the technical working out of that was a real achievement. So finally, you get some antiprotons that you can accelerate. You put them into the main ring at CERN, going one direction, and the protons going the other direction. You collide them, and you try and make W and Z bosons. So now what I'd like to do is to tell you a little about the theory of how you detect these W's and Z's and how you measure the masses. Now I think in the slides, here, excuse me, I should be better prepared. In the slides for this lecture, I have some pictures of W and Z events. We ought to figure out what W's and Z's decay to and how you see them. But roughly what you can imagine, here, please excuse me, is that W's can couple to UD bar, or they can couple to a lepton and a neutrino. And so in a proton-antiproton collider, you're going to see the reaction pp bar, and then inside that there's a ud bar collision, which makes a W, and then you can try and visualize that by looking for a lepton in the neutrino. So what you should see, if this is a very heavy particle, this lepton will come out with a in a random direction with a momentum which in its center of mass frame is about 40 GeV, according to this estimate. So if I boost that, the transverse momentum is still of that order. So I'm looking at events where a lepton is coming out in some direction. It has a transverse momentum, which is of order 40 GeV. On the other side, there's a neutrino, which you don't see, and then lots of soft tracks with relatively low transverse momentum. And for the Z, that might be produced in a UU bar collision. It might materialize as L plus L minus. And so you should see some similar events of the same character, with lots of soft tracks but no very hard tracks, a lepton and an antilepton whose momentum roughly balances and which should add up to this number of 90 GeV. And so in today's lecture, in the first slide, there are actually some pictures of these events from the UA1 experiment, the original discovery. And these pictures are done on the Lego plot that I think we've talked about already. It's a plot of phi versus theta, with the towers being the height of the transverse momentum. And in the top, you can see some really striking events that have exactly this character. And in the bottom, two very striking events that have this character. OK, well, now you can make some tests of whether these mass predictions are correct. And indeed, one doesn't do so badly. For here, you can just basically add up the momentum of the lepton pairs and get an estimate of the Z mass. And indeed, what was found was rather close to about 92 GeV is what was found. Over here, you have to work a little harder because you don't see the neutrino. You need some method of estimating where the neutrino is. But there's actually an interesting way to do that, which I guess I'd like to explain to you. So we don't know, we only know the L plus. This is coming from a collision of U and D. The U and D are coming out of the parton distribution of a proton and an antiproton. So we know what the momentum of the proton is, but we don't know what the momentum of the U and D quarks are. So we don't know in what frame the W is being produced. All we see is one product. However, we can still do something with that. And let's try and do it in the following way. Let's first go to the frame in which the W is at rest. Then the momentum of the lepton, and let's say so what do I want to do? I think what I'd like to do is to go to the frame, sorry, a different frame, where the lepton is being emitted at 90 degrees. In that frame, the lepton momentum is, the energy is exactly, if the lepton is treated as massless, the energy is exactly equal to the PT of the lepton. So this is KT 0, 0, KT. Sorry. KT 0, 0. That's the vector of the lepton in that frame. Now what I'd like to do is to boost to the actual frame of even the lab frame, where the lepton is being emitted also with some longitudinal momentum. And so if I boost to another frame, this becomes KT cosh eta, where eta is the rapidity, kt 0, there's some vector here, kt sinh of eta. So eta is the rapidity. It's the essentially the hyperbolic angle through which you're making the boost. This vector satisfies pt squared plus p longitudinal squared is equal to the square of the energy. And we can write a similar formula for the momentum of the neutrino. There's a different boost from this frame for the neutrino. Sinh eta neutrino. The thing we do know, though, is that the original U quark and D quark were coming in along the axis. They were parallel to the proton momentum. So the transverse momenta balance. So now, from these formulae, we can make a construction of the mass of the W. mw squared is the sum of these two vectors, kl plus k nu squared. Now these vectors are both essentially massless, so that's 2kl dot k nu. And if you take that dot product, there are two pieces of it. First of all, there's a kt squared from that dotted into that, and it's actually a plus because of the minus sign there. And then that times that minus that times that is kt squared times the cosh of the difference in the rapidities. Sorry, it's just that. And there's a 2 in front of the whole thing. Now this is a very interesting expression because a cosh is always greater than 1. And so this is then greater than or equal to 2, oh, please. Please excuse me. I think I made too many approximations here. Let me just finish this. This is greater than or equal to 4 kt squared. So if I were to measure the kt squared, I'd get already an estimate of the mass of the W. Now we can do slightly better than that. In principle, the W could be produced with other stuff. So it could be produced with stuff that carries off transverse momentum. And so I can modify this expression in the following way. I can measure the kt of the electron. I could, in principle, measure the kt of the neutrino. I'll tell you how to do that in a moment. Then this expression would be modified in the following way. What I would get is the kt of the electron, the kt of the neutrino here. And here I would get 2 kt of the electron times the kt of the neutrino minus the kt of the electron dotted into the kt of the neutrino. So if these are roughly back-to-back, you get the expression that I had here a moment ago. How do you measure the kt of the neutrino? Well, the neutrino is supposed to be the only thing that's missing in this event. So if you just add up the kt of everything else, including all of these hadrons that are produced, and you subtract that from 0, you get the kt of the neutrino. So the kt of the neutrino is actually the kt which is missing once you've added up everything visible in the event. In principle, you could also get the longitudinal momentum of the neutrino that way, except that a lot of the stuff is going in the way forward direction, where you remember these detectors aren't sensitive. You can't measure things that go right down the beam pipe. And so you can't get the longitudinal component very accurately, but you can get the transverse component very accurately, including its vector direction. Now, this is an inequality, but it's an interesting one. This quantity here is called the transverse mass, and it is a lower bound to the mass of the particle. So if I now get a lot of W events, and I make a histogram of transverse mass, that distribution should be a distribution like this, which cuts off at, so this is the MT of the W. This should be a histogram like this that cuts off at the mass of the W. And so, very interestingly, I can measure the mass of a particle that contains invisible decay products by measuring a distribution like this and looking for its endpoint. If the W has a width, this will spill over a little. And then, of course, if you miss some hadrons and you mismeasure the neutrino momentum, it'll spill over a little more. But you can do it by detailed simulation, you can correct for those effects. And so you can get a very accurate mass of the W. So on the next slide, this is page 3 of the PDF, I show you some modern versions of this from the CDF experiment. This is the transverse mass distribution for events at the tevatron. This is now, I think, 2 TeV in the center of mass. And you can see that that distribution looks exactly like this. It runs up and then it cuts off really rather sharply at a position that defines the mass of the W. And so from this, you actually get an estimate of the W mass. And if you do it really carefully, it can be fantastically precise. MW equals 80.420 plus or minus 0.031 GeV. There may be a better number even today. So that number is in very good agreement with the estimate that we got from the low-energy neutrino scattering. Now, you can also produce the W in electron-positron annihilation. You have to go to high energy. You'd need an energy above, as you see, 160 GeV in the center of mass. But that was done at the accelerator LEP. You could produce E plus E minus to W pairs. And then you can look for this in several ways. The W will decay, as I said, both to L nu and to 2 quarks. So each W can decay either to 2 jets or L plus neutrino, so a lepton and missing momentum. And I think I've put a couple slides that show these decays in as the next couple pages. The first one is a very striking event from LEP with an electron, a muon, and something obviously missing. The second one is an event with 2 jets, as you see. And then up at the top, there's a single track, which is actually identified as a tau decay product. So QQ bar and the lepton is a tau in that case. And on the next page, there's another one which has a 4-jet event, of which the pairs of jets combine in mass, 2 pairs of jets, each combining in mass to a mass of about 80 GeV. The LEP experiments, then, if you have a 2-jet event, you can try and do calorimetry on that 2-jet system and just look experimentally what is the mass of that 2-jet system. And the people who do that most accurately from LEP come to a number of 80 point, here, I have it down here, 376 with a similar error. So this is from the tevatron. This is from LEP. These are 2 completely different techniques. Please notice that the error is at the 10 to the minus 4 level. So this is a number, some fundamental constant of nature, which we seem to know extremely well. For the Z, you can also get the mass that way, but there's a more accurate way to get the mass. And it's part of a program that I'd now like to explain to you. So the W, its decay properties are relatively simple. You go to one of these or the other, and everything has the strength of the weak interaction coupling. The Z has a more interesting decay pattern. And I'd like to spend a little time working out the decay pattern of the Z. Maybe actually it's simplest to begin with the decay pattern of the W just to warm up, and then we'll talk about the Z. So what I'd like to do now is to compute the width of the W, and in particular, the partial width of the W into various species. So the matrix element for W decay, it's given by the inverse of this Feynman diagram. W going to, let's say, UD bar or L nu. Maybe this is the easiest one to compute. It's I times G over the square root of 2 times the polarization vector of the W times U bar for the neutrino, gamma mu V for the lepton, and these are the left-handed spinners. And actually, this thing here, we've studied that before. It's a current. And so we computed that when we discussed E plus E minus annihilation. It's going to be basically the square root of 2E, where E is the energy of those final particles in the W frame, times epsilon times the square root of 2, well, times, let me write, epsilon of, let's say, the lepton direction, where epsilon is one of these vectors 0, 1, I, 0, plus or minus I along the axis of the leptons, depending on basically whether you take it with respect to the L, which has right-handed polarization, or the nu, which has left-handed polarization. To compute a total rate, I don't actually have to get that straight, fortunately. We can just square this. And what I want to do is sum over the polarizations of the W. So when I sum over the polarizations of the W, I'm summing this over 3 directions. I get the square of this vector, which has a factor of 2. I get this 2e. 2e is actually the mass of the W. This thing here gives me a g squared over 2. And that's it, I think. And so this is just g squared mw squared for every species. The decay rate of the W is 1 over 2 mw. I should average over the 3 polarization states. There's a 1 over 8 pi, and there's this matrix element. And I think if I've done everything correctly, g squared over 4 pi is alpha w, which I told you what it was before. It's a number whose value is about 1 over 30. There's left over a factor of 12. There's an mw, and that's the value. So this would be the rate for w going to, let's say, e nu, or in general a lepton. Let me write e nu, or mu nu, or tau nu. If I send the W into quarks, UD bar, there's an extra factor of 3 because I have to count colors. And you remember there's this 1 plus alpha s over pi, etc., another 4% enhancement. If you add these all up, we know all the numbers. You can actually get the value. So basically, it's 3 of these and 2 of these. And this number here is 3 times 1 and a 4% extra. So roughly what's going to happen is that it's going to decay half and half to lepton, sorry, 1/3 of the time to leptons, 2/3 of the time to quarks, equally to the 3 lepton species, and equally to UD, and the other possibility is CS bar. And then the third possibility in the standard model, TB bar, is forbidden because the top quark is heavier than the W. That one is not energetically allowed. So at the end of the day, you find the W decay pattern. Gamma W, if you put in the numbers, turns out to be 2.1 GeV. The branching ratio of a W to a lepton turns out to be about 11%. The branching ratio of the W to UD bar or CS bar turns out to be about 34%. And if you add up 2 of those and 3 of those, you get 100%. So that accounts for everything. Okay. Now, what about the Z? Well, the Z, it's a very similar story, except we have to be a little more careful about the coupling constants of the Z. For the W decay, the coupling constant at this vertex was G over the square root of 2, and that was very easy to account. For Z decay, we have to take the formulae from the previous lecture. The Z decays to some fermion-antifermion pair. Let me consider a left-handed fermion and a right-handed antifermion, although I could also do it the other way around. The coefficient here was the square root of G squared plus G prime squared. So I can also write that as E over sine theta W cosine theta W. And then there was the Z charge, which, remember, we worked out last time. There's a piece that comes from the SU2 and a piece that comes from the U1, which we could put together in this framework. So the isospin under SU2 and the electric charge of the species. Now, this leads to some weirdness in the pattern. And so let's just make a little table of these things. And you'll see what I mean. So there's the left-handed particles and the right-handed particles. And there are 4 kinds of particles with different quantum numbers, namely the neutrinos, the leptons, the up quarks, and the down quarks. So for the neutrinos, only the weak interaction only couples to left-handed neutrinos. Let's call this quantity here QZ. Let me make a table of the QZs. This is plus a half, and there's actually nothing in that column. Or it's 0 if there are right-handed neutrinos in the world. The Z doesn't couple to them. Here I have minus a half plus SW squared, and here I have SW squared. Here I have a half minus 2/3 SW squared, and here minus 2/3 SW squared. And here I have minus a half plus a third SW squared, and here a third SW squared. So the first thing you can do is just take the sums of the squares, and that gives the relative branching ratio into each of these kinds of species: neutrino, electron, up quark, and down quark. And then it's repeated for the other generations, except for the top quark, which again is too heavy to be produced in Z decays. And so let me do that exercise in a moment. The other thing that you can do is look at the difference between these quantities. So SW squared is about 0.23. It's close to a quarter. And so this number here, in absolute value, is a little bigger than a quarter, and this one is a little smaller than a quarter. So the Z decays with almost the same strength into left-handed and right-handed electrons, muons, and taus. On the other hand, this number here is rather close to a half, and this number here is very small. So the Z decays dominantly into left-handed up quarks as opposed to right-handed up quarks. And then in the bottom line, it's even worse. This is a third times a quarter, so this is a 12th. So this number here is a sixth, and this number is very close to a half. And so you're even more dominantly decaying if you have down quarks, strange quarks, or bottom quarks into the left-handed species. And that has a consequence which can actually be tested experimentally, as we'll discuss in a moment. First of all, let's just get the Z branching ratios. The formula for the Z branching ratios can be derived basically just exactly along the lines of the derivation here. This factor of the square root of 2 is missing. So there's going to be an alpha weak over 6. There's an extra factor of the cosine squared of theta w. There's the mass of the Z. And then what comes in is the qz left squared plus qz right squared. That is the square of this factor plus the square of this factor. And so if you now put in all the numbers, what you get is the following. There's this prefactor again, alpha z over 6 cw squared. And let me just evaluate all these factors numerically with the value sw squared is 0.23. So there'll be 3 neutrinos. For the neutrinos, it's just a quarter. There'll be 3 kinds of leptons. For the leptons, this squared plus this squared comes out to about, it's like a quarter squared plus a quarter squared. It comes out close to an eighth. So this is for E, mu, and tau. For U and C, I'll get 2 times 3 times this extra factor. So it's 3.1, actually. And then the number that you get here is 0.144. And for D, S, and B, I'll get 3 times this number 3.1 times the value is 0.185. And so now we're actually in good stead to predict all the branching ratios of the Z plus the total width. We just evaluate everything that's in that formula. I think if you actually evaluate this formula, you come to 2.49 GeV. And then if you look at the relative sizes of the formula, you get the branching ratios. So the branching ratio to a neutrino pair is 6.7%. The branching ratio to, let's say, mu plus mu minus is 3.1%, 3.3%. The branching ratio to UU bar, or CC bar, maybe I should say, is 11.9%. The branching ratio to DD bar is 15.3%. The branching ratio to BB bar is this number minus 2%. And that 2% comes from a funny effect. I told you that the top quark was too heavy to be produced directly in Z decays, but it can be produced virtually. And it's produced virtually through some diagrams that look like this, where you make a top quark, you exchange a W, and you end up with BB bar. And then for gauge invariance, you also need this diagram. And if you add those up, those give a minus 2% correction. So in fact, the probability of making BB bar is slightly less than the probability of making DD bar by a correction associated with these diagrams. So another thing that you can predict is the number R sub B, which is equal to the probability of making BB bar divided by the probability of just making hadrons, making any kind of quark. And this turns out to be, I think, 0.216. So it's a little greater than a fifth because the down quarks are more populous than the up quarks. But it's lower than it would be without this correction. Without that correction, it would be 0.220. OK. Well, now, what does experiment say about all these things? So how do you do the experiment? Well, if you want to create a beautiful sample of Z decays, what you would presumably do is collide electrons and positrons in a very controlled way. So this is what was done, actually, at the accelerator LEP at CERN and also at the SLC collider at SLAC. You make an electron beam, you make a positron beam, you collide them, you make the Z, you let the Z decay, and then you just look and see what happens. The Z appears in this process as a resonance. So, of course, there's also the virtual photon process. But when you're exactly at the Z mass, you have an enhancement, essentially the square of the propagator. And if you just plug in the numbers, this is about a factor of 1,000. So you have a huge resonance that appears in E plus E minus annihilation when you tune it exactly to the mass of the Z. So in the slides, I have some measurements of this resonance shape. And so what page is that, please? So page 9 and page 10. You can see some measurements of the resonance shape. Page 10 is maybe the most interesting. That's close to real data. And if you stare very hard at that slide, you can see that there are actually error bars on the points. Yes?
What does the width appear in the propagator?
Because if the width weren't there, there would be a pole. But a decaying particle can't have a pole on the real axis. A decaying particle is indefinite because there's an uncertainty in energy, which is h bar over the lifetime. So this is basically that's what the width is. And so what happens is that if a particle is unstable, its pole gets pushed down below the real axis. So the propagator is this, right? But if you have the particle being unstable, and you include the diagrams that include the decay into the decay channels, then this expression gets modified to this expression. So the particle gets moved off the real axis. And what you see for real momenta instead is a Bright-Wigner, so-called Bright-Wigner distribution like this. So if you sweep through these energies, what you'll see is a big resonance like that. The height of the resonance, I should have left something that's 1 here, is essentially a measure of the width. And then the width in energy units, the width of the resonance, is exactly that. Now, in the real situation, there are corrections to this simple picture. First of all, the width, first of all, the coupling of electrons to the Z is affected by, let's say, Z photon, even W exchange can appear here. And so the height of the cross-section is slightly corrected by these kinds of radiative corrections. We've already expressed that when you radiate gluons, you get a correction to the rate of the decay for quarks. That effect is already included in these numbers. And there's one more interesting correction, which is that just like for quarks radiating gluons, when electrons radiate photons, the energy of the electron goes down slightly. So you need a higher energy to produce the resonance. So because of this effect, actually, the resonance doesn't quite look like that. It is spread out and kind of sloughed over to higher energies. And if you look at that plot on page 10, you can see that the resonance is visibly asymmetric in this way. And then the curve that's fit through those points is the standard model theory, which includes all of these effects. So basically, this measurement is testing all three of the interactions of the standard model, weak, electromagnetic, and strong. And it seems to get the right answer. So experimentally, the numbers are the following. The mass of the Z is 91.1875 plus or minus 0.0021 GeV. So this is now at the 10 to the minus 5 level of accuracy. And the width is 2.4952 plus or minus 0.0023. So it's in very good agreement with this estimate that we made up here. And actually, even such that you might think that it's learning about this effect, although I'll have something else to say about that effect in a moment. Sorry. Now, the width that we measure here includes the effect of invisible decays. Even the decays that we don't see, so the height of the curve reflects only the visible decays. In fact, typically this curve would be made for only the decays to hadrons. But the width of the curve reflects the invisible decays. And if I draw the curve like that, you can see that if I added additional invisible decay modes, then the curve would be slightly broader and less high. And so if I fit for this effect, I can actually figure out how many invisible decays the Z is making. If you like, you could parameterize that as in terms of the neutrino cross-section. That is, I could write that the gamma of Z for invisible decays is equal to the decay for a neutrino that I've written there times the number of neutrinos. And if you now fit that distribution varying the number of neutrinos, the number you get is 2.984 plus or minus 0.0082. So the Z decays, it seems, exactly to 3 species of neutrinos, no more, no less. Okay. Well, finally, I should tell you a little about this. No, I don't think I included those slides. But I've told you enough already that you can understand that this measurement here can be tested directly. I think I showed you in the lecture on experimental methods a Z event with specifically B jets that we had observed because you have a jet-like event, and then you go very close to the center, and you notice that there's some tracks that form a vertex a centimeter away from the interaction point, signaling the long lifetime of the B meson that flew from here to here. And I think in that event there was even such a vertex on the other side as well. So by trying to measure the specifically B events and then looking at their ratio with respect to the whole event sample, you can measure this number. And the measured value is 0.2169, 21629. I'm sorry, plus or minus 0.00066. There we go. So in fact, one actually understands the B branching ratio of the Z well enough to say these diagrams are present, and there are no non-standard diagrams which are of the same order. Okay. Well, now there's just one more thing that I wanted to tell you about in terms of the Z decays, which is this asymmetry that I pointed to a moment ago. So you remember I showed you in that table that the Z decays asymmetrically to left-handed and right-handed standard model particles. I could compute the following quantity. A sub f is equal to the Q to left-handed particles minus the Q to right-handed particles squared divided by the sum. And this is predicted in the standard model for each species of quark and lepton. So for the neutrinos, from the formula that I wrote before, this is 100%. It never decays to the right-handed guy because the Z doesn't couple to it, or maybe it doesn't exist. And the left-handed guy is all there is. For the electron, you remember the QZ left is a little bigger than a quarter, and the QZ right is a little less than a quarter. And when you work it all out, this number is about 15%. For the up quark, the number is about 67%. And for the down quark, the number is 93%. So it's really very striking. Every species has its own parity asymmetry in Z decays, and it's interesting to test all of these numbers separately. And so to do that, what we need to do is to look specifically at lepton decays, look specifically at something we can identify as an up quark. What's used as a proxy here is the charm quark. And here, something we can identify specifically as a down quark, and what's used here is the bottom quark. So let's talk a little about those measurements. So if we want to think about Z going to L plus L minus, what I want to do is to ask how I can measure the polarization of the lepton that comes out of Z decays. And there are basically three ways to do that. One I'll explain. Well, there are three ways to do that, of which two really get you very high precision. If you look at an electron, there's not much you can measure about an electron in a high-energy physics experiment that tells you its spin or helicity. For a muon, well, if you stop the muon, but these detectors typically aren't big enough to stop muons. But with the tau, you can actually do something. So the tau is an interesting particle. It has a pattern of weak decays that actually you can work out with the standard model. I think actually I put it as an optional problem on the third problem set to just work out the complete systematics of tau decays. It's kind of fun. The tau can decay like a muon to an electron and tau neutrino and an electron neutrino. It can decay to a muon and an anti-mu neutrino. These decays, the formulae are exactly modulo the increase in the tau mass. Remember, this is a particle of mass 1.7 GeV. Sorry? Okay. Modulo the change in the mass. Here the formulae are exactly those that we discussed for mu decay on Friday. The tau can also decay to a tau neutrino and a pion, a tau neutrino and a rho, a tau neutrino and a particle called the A1, which is an axial vector meson. And then there's a list of other decays. Basically, it can decay to a neutrino plus anything you can produce from a current. The current is the J minus V minus A. So the axial, the odd parity part, can produce this, and the even parity part can produce that. So in every case, you know exactly what the detailed dynamics is of the decay, so that gives you some polarization information. The simplest case is with a pion. We start with a tau in its rest frame with, let's say, the spin oriented in this direction. The tau now decays to a neutrino and a pion. The pion is spinless. The neutrino is always left-handed. So what that means is that in this frame, the neutrino must decay backwards to conserve angular momentum. The distribution is actually 1 minus cosine theta where theta is the angle between the neutrino direction and the tau momentum. You can work that out very easily. If you now boost this whole system so that the tau is in very relativistic motion, cosine theta becomes the fraction of the tau's momentum carried by the neutrino. And so d gamma dz is proportional to 1 minus z. And now let me try and get everything put into the right orientation. If I have a tau which is right-handed, that decays to a slow neutrino and therefore a fast pion. So the right-handed tau has a distribution, and I put z of the pion now. This is proportional to z of the pion. And for a left-handed neutrino, d gamma dz pion is proportional to 1 minus the z of the pion, where z is the momentum of the pion divided by the energy of the pion divided by the energy of the tau in a kinematics where everything is going forward very fast because the tau is very relativistic. Okay, well now you can measure the distribution of pion energies in z goes to tau goes to a single pion event and try and fit it to a sum of these two distributions. And that's shown on page 11 on the left-hand side in the slides. And what you can see is that the data are really consistent with a linear slope. The data are the little crosses. It's consistent with a linear slope in the distribution. So it's a linear combination of this and this. And it's clear there's more of this than this. And if you extract the polarization from this measurement, you find A tau is equal to 146 plus or minus 1465 plus or minus 0.0032. So you get a number that is very consistent with this 15% estimate, which comes from the standard model. The picture next to it on that slide shows the analogous calculation for tau to mu decay. You remember we discussed in detail the polarization structure of the tau of the mu decay to E last Friday, you can use the same analysis to analyze the polarization dependence of the muon distribution in tau to mu. And then you can make the curves that are shown on that slide. I won't go through it in detail. Now, there's another much more tricky way to measure the polarization asymmetry of the Z. And that's just to make a polarized beam. So you make a left-handed electron beam or a right-handed electron beam, and you measure the total cross-section from making Zs. So here you're looking at the production rather than the decay, but it's the same vertex. And again, this one is proportional to the q left of the Z squared. This is proportional to the q right of the Z squared. So in the same way, you can measure the tendency of the Z to favor production from left-handed rather than right-handed electrons. The tricky part is how you make the electron beam. If you have electrons in a circular accelerator, then those electrons radiate synchrotron radiation. Their energy goes up and down. They go through some resonances. They very rapidly get depolarized unless you're exquisitely careful, which it's really hard to do in a machine the size of LEP. That's a 27-kilometer ring of magnets. A better strategy is to use a linear accelerator, because if you accelerate a particle along a line, then that process actually preserves the polarization. And so if you create low-energy polarized electrons and accelerate them in a linear accelerator, and then immediately annihilate them before anything has a chance to happen to them, you can preserve the polarization. So that experiment was done at SLAC. Well, I'm from SLAC, so I provided a couple slides here. The first one is a layout of the SLAC linear collider that did the experiment. The next slide, this is page, what is that? Page 13, has a diagram of the polarized gun. And the very cool thing about it is right in the middle of the slide, what you do is you bring laser photons onto what's called a strained gallium arsenide cathode. So it's basically gallium with a little arsenic which bends the lattice, and it separates the upspin from the downspin electron bands. And then you hit it with exactly the right energy that you can kick out upspin electrons without kicking out downspin electrons or vice versa. And the way you control that is with something on the laser, a polarizer on the laser, which is an adjustable circular polarizer. So you hit this thing with left-handed or right-handed laser photons. This is something called Epochal Cell. So you put some kind of coded signal on it. Pluses or minuses if you want left-handed or right-handed circular polarization in a random pattern. And then the electrons are made. They propagate 3 miles down the accelerator. They eventually annihilate with positrons. You get a change in the cross-section. The cross-section changes randomly, and then you look at the correlation between that random change in the cross-section and the coded pattern that you put on this cell. So lots of systematic errors cancel when you do the experiment this way. And you get a number for the asymmetry, which is 0.151 3 plus or minus 0.002, which is actually the single most accurate measurement of these Z asymmetries that exist. Although, frankly, the tau comes pretty close to that. This is actually kind of interesting because you can take the formula that I wrote here. Remember, this number comes because this is a little greater than a quarter and this is a little less than a quarter. So an approximate formula for SW, A lepton, is that it's equal to 8 times a quarter minus SW squared plus some relatively small term of order SW to the fourth. And so this asymmetry measures the deviation of SW from a quarter, and it measures it very accurately. So if you put together all of these experiments, we actually now know that this SW is not 0.23, it's 0.2315 with an accuracy in the fourth decimal place. 3153 plus or minus 0.00016. So we really have now a very good handle on the properties of the weak interactions. And then if you like starting from this extremely accurate value and going back through all the standard model, all of the standard model data is basically consistent with that. Let me tell you about one more of these things, and then I'll quit. To measure, now we know that this number is 15%. Can we measure that this number here is maximal? Well, that you can do with forward-backward asymmetries. And again, this is something that I explained to you the basic physics of it in the lecture on E plus E minus annihilation. You just have to remember that when you have an electron-positron going to a left-handed quark, this differential cross-section goes like 1 plus cosine theta squared for angular momentum reasons. So it's extremely peaked in the forward direction. When you have right-handed electrons going to left-handed quarks, this distribution is 1 minus cosine theta squared. So this distribution is extremely peaked in the backward direction, again for angular momentum reasons. So if I'm able, as I've just explained to you, to produce a beam of polarized electrons, why don't I just go look at where the bottom quarks come out, and then I can test that prediction. So the data for that is given on the next slide. You can't quite measure this perfectly because it's not always possible to tell which is the B and which is the B bar. Of course, if the B is forward, the B bar is backwards. And if you confuse these, it's not going to come out perfectly. But what you see is that the effect is really very dramatic. If you have left-handed polarized electrons, the bottom quarks come out very dominantly forward. Right-handed polarized electrons, the bottom quarks come out very dominantly backward. By the way, the difference between the normalization of those two curves that you see there is the 15% asymmetry from the production that I was telling you about a moment ago. And so one obtains the value AB is equal to 0.923 plus or minus 0.020. So that number is very consistent with the estimate from the standard model that I have almost maximal polarization asymmetry between B's and B bars. So on the, I guess, the next slide, which is the last one I'm going to talk about, there is essentially just a list of all of the precision electroweak measurements. And what you see graphed there is the number of standard deviations of deviation from the standard model with the best fit value of SW squared. And you see basically that with a couple of exceptions, which I guess, as was pointed out, you always expect on a plot like this, the agreement is just fantastic. At the basically 4 decimal place level of accuracy, this Glashow-Weinberg-Salam theory explains all the details of Z decay and Z production as well. On the very last slide, I have some higher energy data, which I guess if any of you want to talk about that, we can discuss that separately. And now we're really almost done the standard model. There are just 2 more topics. The first one is that we still haven't put the masses for the quarks and leptons into the standard model. So I have to tell you about that next time and talk about some consequences of that. And then finally, I want to give you a lecture on the top quark. And then on Friday, we'll talk about some things that aren't known. So see you tomorrow.